Okay. Got the right camera, the right microphone. Seems to be working. Okay, here we go. All right, let's talk about the Doppler effect. We'll flip to the first page here. We'll fill our notes in. We'll define the Doppler effect. The Doppler effect is when relative motion occurs between a source and an observer of waves. So we'll see some examples here. It's any type of wave can experience the Doppler effect. We have to have motion, though. We haven't really seen this before. We've seen things create waves and other things experience the effect of those waves. But what if those things are moving? Either the source of the waves or the thing that's observing the waves are moving. And what makes it be the Doppler effect is we end up with a change in observed frequency of the wave. So the properties of the wave, the frequency of the wave will change when motion is involved. And frequency, depending on what kind of wave we're looking at, it could be different things. If we're thinking sound, for instance, the pitch of the sound can change. If it's light, we're talking about the color, the wavelength, the frequency of the light. So one of the most common examples of the Doppler effect is the sound you experience when something moves past you and it's making noise. Whether it's like a freight train or an airplane, or we have a police car going past this person, and it makes a relatively high-pitched sound as it moves towards the person. We'll say they hear a high frequency as it moves towards the person, and this thing's moving in this direction. So we'll say the police car is the source of sound. It's creating sound waves. And then the police car has some speed, and we'll call that speed u, just like our SUVAT equations, the velocity of the object. This is the speed of the source, us. Okay. And then this guy right here is the observer who's hearing the sound waves. Okay. And here the source is moving towards him, so he hears a high-pitched sound. And then as the source of sound continues to move past him at the same speed, now as it moves away from him, he hears a lower frequency sound. So when you get into the activity, you'll get to hear some examples. So there's some files where you can hear what this sounds like. You've probably heard it in everyday life as well. So I got it spelled out right here. So something heading toward you makes the and then the pitch drops as it goes past you. That's a good example, right? Okay. So why is this? Why does the frequency of the wave change as it moves either towards you or away from you? Well, it's helpful to think about what those waves look like as they move away from the source of the waves. So suppose we have a speaker that's playing sound, and if the speaker is sitting still, the sound spreads out uniformly in all directions. It just heads at the speed of sound in all directions, and no matter where you are in relation to the speaker, the waves sound the same. Okay? On the other hand, though, if the speaker is moving, we now have two speeds involved. We have the speed of the source, so that's the us, and then we also have the v right here, which is the speed of sound. So usually the speed of sound is pretty fast, right? It's about over 700 miles an hour. A speaker on a skateboard is going to be going much slower than that. So it's not going to be traveling as fast as the waves it's creating. So the waves will still get ahead of the object, but they end up bunched up together. Okay? So you can see that each of the wavefronts is still a circle. Okay? The sound is still spreading out. Really, it's a sphere because it's spreading out in 3 dimensions. But what ends up happening is that the center of the circle is moving to the right. Okay, here the center of the circle, they're all concentric, right? Because the source stays in the same place. But when, right where my pen is right now was where the speaker was when it made the first circle. It's at the center of that one, but then it shifted over a little bit when it made this circle, and then it shifted over a little bit more when it made that circle. Okay, and so as it moves, what it does is it ends up bunching these circles together. So we can see visibly that the spacing between the crest is really small. We have a short wavelength, a short lambda over here, and that the waves are really spread out behind, so we have a long wavelength over here, behind the source. So if the source was moving towards you, you'd see waves that are very close together, and if it's moving away from you, you'd see waves that are spread apart. Okay? Now, the speed of those waves is the same. It's always the speed of sound, and since we know that the speed of a wave is equal to the frequency times the wavelength, and they all have the same wave speed, What's going to happen is as the wavelength gets shorter, if it still has to be equal to the speed of sound, that means the frequency has to get higher. So somebody in front of this speaker is going to get a higher pitch sound. They get the high frequency. And somebody behind the skateboard gets the lower pitch sound. They get the low frequency as these waves get distorted. So one of the things that's unique about this particular activity and lecture is that the Doppler effect is part of the SL and the HL curriculum. But the SL only needs to know it qualitatively. So you just need to understand that the frequency gets higher as something moves towards you and it gets lower as it moves away from you. HL is responsible for the formula. So this is only on the data sheet for HL, and you'll have to solve problems quantitatively. The formula for the Doppler shift of the frequency is written like this. So you can both put it down in your notes, but only HL will have to use this to solve for things. Okay, so F prime equals F. We'll unpack what these things are in a moment, times the quantity V over V plus or minus US. This is the way it's written on the data sheet. You don't have to memorize this one. So let's just unpack this, what these different terms mean in this equation. So, of course, F is a frequency of the sound. Okay? So what we're solving for with this equation, F prime, okay, this is the observed frequency. So the source of the waves is moving. This is the question, what does the listener hear? Do they hear a high-pitched sound? Do they hear a low-pitched sound? We could use this equation to solve for the sound that they actually hear. Okay? This frequency right here is the source frequency. So in our police car example, it's whatever the frequency of the siren is. Okay, and then we've got some various speeds over here. Okay, so we notice see the variable V shows up twice and then U shows up once. V right here is the speed of the waves. So if we're talking about sound waves, and so that these are both the speed of the waves. It's in the numerator and in the denominator. Okay, and then US we already said that's the speed of the source. And we've never had to use this equation before because in all the problems we've looked at, waves, the source of the waves has just been sitting still and it's just been sending waves out. Okay? So when that's the case, if the source isn't moving, if you look at this equation, if US is equal to 0, then if it's just 0, the fraction just ends up being V over V, which is 1. Okay? And the observer just hears whatever the source is putting out. Okay? But as the source starts to move, this starts to get distorted. Okay. Now, what's funny about this equation and the way they write this on the IB is that this equation can be used for both the case of the source moving towards you or away from you. Okay. And you have to decide whether it's plus or minus. You pick. And it's going to depend on whether the frequency should be getting higher or should be getting lower. So, and this is something both HL and SL should be able to do, is recognize when a source is moving away from you means lower frequency and moving toward you means higher. Okay? So let's say we're doing a problem and something's moving away from us, then that means that F prime needs to be something that's smaller than F. Okay? So then that means that this needs to be a plus in the denominator so that it has a big denominator, which makes, once I multiply by F, I get something smaller than what I started with. Okay? Whereas the minus would correspond to moving towards me. Now, one thing that I said earlier about the Doppler effect is, and really we've said all along, is that motion is all relative. When you see something moving, it's always measured with respect to something. So what's really fascinating is that in the example on the previous page about the police car moving, okay, this guy, as the police car moves towards him, hears the high sound and then the low sound, but for the driver, the policeman driving in the car, okay, even though the source is moving, it's not moving in relation to him. So the person in the police car hears the same thing as if the car was just parked and at rest, okay, because the speaker isn't getting close to or farther from his ear. So it's all about relative motion. So in that case, let's suppose the car was parked and our observer was the one that was running to the left or moving to the left. That's kind of the same thing, right? Moving toward the source. So it's just about getting closer or getting farther. The same effect should happen if we have a moving observer and the source sits still. So here we have kind of a picture of that. So suppose Suppose we have two speakers that aren't moving, but the observer is moving, okay? And looks like she's running to the right here. It'd be weird if she was running backward. So we'll call this one UO, not 0, but O. This is the speed of the observer. Okay? And her running toward the speaker is kind of the same thing as the speaker moving towards her. Okay? And so the same effect happens. She gets a high frequency. She hears a higher pitch sound as she runs toward the speaker. Now, technically, it's for a slightly different reason, because as you can see in the picture, these waves aren't closer together. They have the same wavelength on both sides. But what happens is she gets more of them per second, okay, which is what frequency is, right? If she just sits here and lets the waves hit her so many per second, that's one frequency. But as she runs into the waves, she's going to reach them faster than if she just stands there waiting for them. So it's less time per wave, and she gets the higher frequency. The opposite effect happens over here. She's going to hear a lower frequency as she runs away from this source, because she's running away from the wavefronts. It's going to take longer for each wavefront to reach her. Okay, so we'll say that the observer sees, and I put sees in quotes because it's sound and you can't see sound waves, but she experiences the waves with the same wavelength. They don't have different lambdas, okay, but she still gets a higher frequency from the source she moves towards. So the IB data sheet, again, this is unique to HL. Gives us an equation for what if the observer is moving instead of the source is moving, and it looks very similar. Okay, F prime equals F. Again, we have a fraction here. We get a V, but this time in the numerator I have plus or minus, and the V in the denominator here. And so on the IB data sheet, they don't designate what these different things are. But you have to recognize that if the observer is the one doing the moving, then you're dealing with the UO, and if the source is the moving, it's the US. Okay, and again, you have to pick whether it's a plus or minus, whether it's making the frequency higher or lower. It's possible that you could have a problem with both the source and the observer moving, but IB limits itself, and they don't give you, they only have one or the other moving. Okay, in case you're curious. And I'm not sure why they didn't just do it this way on the IB data sheet. You don't even have to write this down if you don't want to. But really the complete way of writing this equation would be V plus or minus to do it this way. And that would encompass both cases, where you could have any adjustments for the observer moving and the source moving. I don't know why they didn't just write it the one way, but they write it two different ways, and they limit themselves to the cases that I've boxed in there. We'll look at a couple example problems there. So that everything we've said has been particularly about sound, but the same effect happens to all waves, and so light waves as well. For an object emitting light, the frequency of the light, and therefore the color of the light, can be shifted. And they give us an equation, and this equation is for SL and HL. So SL students might have to solve a problem using this formula here. And we haven't gotten into relativity yet for things that are starting to move close to the speed of light, but for objects like regular objects, like headlights of a car, or something that's moving much slower than the speed of light, there's a Doppler equation for the shift of light. And this one's on the IB data sheet as well. And it's written like this. And we won't really be able to justify this until we learn about relativity. And he gets to learn about that next year. Tanya, you're going to have to take my word for it. So they give us this one on the IB data sheet. We have a little key over here to the right to recognize what these terms are. So the delta just means a change or a shift. So how much has the frequency been shifted? And notice if the frequency is being shifted, so is the wavelength. For light, the shifts in frequency and wavelength, the amount of shift compared to what the actual frequency is for the source giving off light. So usually when we're talking about light, it might be the headlights of a car, the motion of a star through the, as it rotates about the Milky Way galaxy. The light that it gives off, it's proportionate to how fast that source is moving relative to the speed of light. Okay, that it's roughly the same as that fraction. So essentially what you can see here is that the faster the object moves, the more Doppler shift we get for light. Okay, as this the amount of shift becomes closer in size to the frequency itself. Big picture wise, this change could either be an increase or a decrease. So whether the delta F or the delta lambda is getting longer or shorter, it could be either. It could be an increase or a decrease, depending on whether it's moving towards or away from you. And so, for instance, if a star, here we got the sun, it looks like if it's moving away from us or we're moving away from it, the wavelength gets longer, which corresponds to the red end of the spectrum. And so this is called redshift. So objects that are moving away from you and giving off light have longer waves and lower frequency, and they're redshifted. And objects that are headed toward you have shorter waves, higher frequency, and they are blue shifted. And they can literally look more red or more blue based on their relative motion. So that is the Doppler effect. We'll do a few example problems, but first let's just look at some places where you come across it in everyday life. There are lots of places where the Doppler effect is used in technology. One is in ultrasound technology. So in ultrasound technology, you've got the probe. It's non-invasive. You hold it up against somebody's head or against their belly, and you're looking at waves of sound that you send into the body and that bounce back. I'll be right with you, Maya. And anything that's moving towards the probe, the waves are going to get shifted shorter. And anything that's moving away from the probe, they're going to get shifted longer. And you can see that actually shows up here on this image. We get like red blobs and blue blobs. So if we're looking at like blood flow, maybe looking at somebody's heart, I guess we're looking at his head in this picture, but if you put it over somebody's heart, or a lot of times used for like measuring like infant heartbeat in utero, as the blood moves towards the probe, it's going to be blue shifted, and as it moves away, it's going to be red shifted. And you can see that motion of objects inside the body corresponding to that. Pause there for a minute and answer Maya's question. Oh. Do, do, do.